Hello everybody, and welcome to another lecture of 6837. Today we're going to continue our discussion of rendering, and specifically the ray tracing algorithm, by talking about strategies we can use to make ray tracing less painfully slow. So let's get started. As a bit of a review, let's talk about the ray tracing algorithm. Notice it's a bit more complicated than the ray casting algorithm, which is what we started with when we were considering rendering. And the main body of our problem is contained in this trace ray function that we see on the slide here. Now, what does the trace ray function do? It takes in a ray, so just like a arrow pointing in 3D space, and its job is to return the first object the ray runs into and the color of that object. So in order to trace a ray, we have to follow a number of steps. First, we have to maybe intersect all the objects in the scene in order to figure out which one the ray runs into first. And then what we started to talk about in the last lecture is all the different techniques that we might use essentially to gather the color of that ray. Now, there might be a term, for example, an ambient term that just involves the color of the object and nothing else. You might want to iterate over all of the lights and check if you're in a shadow or not. And if you're not in a shadow, then add a shading term based on the light source. And then you might additionally want to use secondary rays to deal with mirrors or transparent objects. Now, notice that each of these three bracketed little pieces of code that I've drawn on the slide here, each of them requires sending more rays out into the universe, right? So for example, if I want to check whether or not I'm in a shadow, I send a second ray out from my intersection point toward the light to see if there's an object in between that point and the light. Or in the mirror case, basically I end up bouncing a ray off of the surface. Or in the transparent case, maybe I have to do some kind of refraction. So what do we need to do here? Well, essentially, in order to ray trace a single pixel, it's not as simple as just intersecting a ray with a scene anymore, but really the number of rays can exponentiate, right? Because every time I trace a ray, I can beget at least 3 more, at least in this simple setup, and potentially many more. And indeed, that often can happen. So for example, last time we showed a simple scene with 3 balls and 3 mirrors. And one parameter that we talked about a little bit in our ray tracing algorithm is a recursion depth limit, right? So for instance, if my ray tracing algorithm isn't allowed to recurse at all, then I don't see the balls at all in the 3 mirrors. If I can recurse 1 time, then I get this sort of 1 bounce worth of light, 2 bounces, and so on. So at the very end of our previous lecture, we introduced essentially a visualization to kind of understand what's going on in the ray tracing algorithm. This isn't really an object that you might want to compute explicitly, but just a way to visualize the computational expense of this technique. So specifically, this is called the ray tree. We have some incoming ray during the ray tracing algorithm, for example, from your eye into the scene. And every time that ray hits an object, it begets more rays, right? So for instance, here are the different categories of rays that we have in our ray tree here. And this includes not just the incoming ray that probably was spawned from the eye into the image, but also reflections, shadows, transmission. You can see there's like total internal reflection happening here. And in each case, we have additional computation that we have to do. So just to get the color of this 1 pixel here, there's a ton of different rays that we have to trace in our algorithm. Each one has to intersect all the objects in the scene. And in fact, for even higher quality images, we probably want to create even more rays than this. So for example, maybe we notice that there's some aliasing in the pixel. So we send a bunch of rays out from the original source point and average their color. We can do that, but then we've multiplied the cost of our ray tracer by the number of rays that we send out in a single pixel to average the color out. And so this leads to all kinds of cool effects. So for example, by doing distributed ray tracing, in other words, basically tracing many different rays, which we can do in parallel, that's perfectly fine. We can get effects like soft shadows, anti-aliasing, where you get rid of these jaggies, glossy reflection, motion blur, depth of field, and many other effects. So let's review what that looks like. So for example, if we talk about distributed soft shadows, well, let's say that I have a light source that is of finite size. So it's no longer just a point, but rather an actual area in space. Well, in that case, that will lead to an effect called a soft shadow, right? Where, for example, points down here receive no light at all from the light source because it's completely obscured by this purple surface. Points in the middle, in the penumbra here, receive partial light that goes from 0 to 100%. And then finally, on the outside, I get the full benefit of the light source. So in order to do that, we're going to have to trace multiple shadow rays because, for example, let's say that we're sitting at this point that's identified on the slide here. Oops. Well, in our shadow algorithm, if we traced back to the left-hand side of the light source, it would tell us that we're not in a shadow. But if we trace back to the right-hand side of the light source, it would tell us that we are in a shadow. And so we essentially want some average of those two values. So one thing we might do is trace many different shadow rays and then compute the fraction of shadow rays that actually make it back to the light. We can do that and we'll get a soft shadow effect if we multiply our lighting by that value. But now notice that it wasn't even just one secondary ray that we needed to launch, but many of them. And in fact, we'll see that in order to get a high quality image, the number of rays that you might need to kind of smooth out that random process could be quite large. We also talked last time about motion blur. So one way we could do that would be to essentially randomly sample the positions of the objects along their paths during the rendering procedure, and then to average the result over many different randomized positions. That can create cool effects like what you see in the image here, but once again, we need more rays. So now the question is, how can we solve this particular problem? That ray tracing creates too many rays. Now, there are sort of two different ways that we could go about this. One would be to reduce the number of rays that ray tracers create, but somehow that runs counter to our nice philosophy that essentially by building a ray tracer, we can get all kinds of cool rendering effects. So instead, in today's lecture, we're going to consider a different way to make our ray tracer faster, which is to reduce the cost of intersecting a ray with the scene. So if you all took 6006 or whatever your favorite algorithms course was, you probably got very used to doing big O style analysis of algorithms, right? Just counting how many steps a different technique takes. And if you try to do that for ray tracing, you'll see that it's like a giant product of a million different terms here. So for example, you need to account for the size of the image. Now for every pixel, you need to launch a ray. There's the amount of time that it takes to intersect that ray with the scene, the average number of recursion calls that you need to make in a ray tree, in addition to all these secondary effects that I just mentioned. The cost of the ray tracer, of course, is the product of all of these different terms. So what will happen is the more cool visual effects that you add to your ray tracer, the slower it'll get. And in a sense, that's expected, right? If you want to make a really beautiful, detailed image with lots of fancy lighting effects, the reality is you're probably going to have to wait. But the question is, how can we reduce this time? And today, we're going to focus just on this box term, which is the number of primitives that your ray has to intersect. So let's talk about that in a little more detail. So currently, if you recall our basic ray casting, ray tracing outline, it's given at the bottom of the slide here. And notice that there's two for loops. One is over every pixel. That for loop is sort of unavoidable, right? Because you want to choose a color for every pixel on your image. But there's a second for loop here, which is over every object in the scene to see if it makes for a closer ray object intersection than the one that you currently have. And this is slow, right? If I have a scene of millions and millions of objects, then I really don't want to intersect array with every single object in order to figure out the color of one pixel on my screen. And so this is typically the bottleneck of a ray tracing algorithm, at least as we described it so far in this course. So today what we're going to do is get rid of this for loop. And instead, we're going to talk about a few different strategies that we can use to reduce the number of ray object intersections. In particular, we'll talk about bounding volume hierarchies, KD trees, and we'll actually mention a third strategy at the end of lecture called ray marching. So these are all basically different strategies that are built on the observation that we don't have to iterate over every object in the scene if we can use clever rules to rule out ray object intersection. So for example, let's say I have a ray and I have a scene composed of two circles and I draw a third circle around both of them. Well, it's pretty clear that if my ray doesn't intersect that large circle, I don't need to intersect it with the two smaller ones. And that's roughly all that we're going to use in terms of logic in today's lecture for how to reduce the number of ray object intersections. So our basic goal here is to reduce this number, and that becomes particularly important for triangle meshes like the bunny that you see on this slide, because in order to get even this really coarse looking shape, notice that the bunny is composed of hundreds or thousands of little triangles, each of which you'll have to intersect with your ray before you can come up with a final color. So here's going to be the basic observation. We're going to make an object that we'll call a conservative bounding volume around our piece of geometry. So for example, with this bunny, we're going to put a giant box around the outside of the bunny with the property that every single vertex and triangle is contained within strictly the walls of the box. Now, when we ray trace our scene, what's going to happen? Well, what we're going to do is we're going to send a ray out into the universe, and before intersecting it with all the triangles of the bunny, we're first going to intersect our ray with the bounding box. And now we have to be a little bit careful with our logic. What do we know? We know that if a ray does not hit the bounding box, it just whizzes right past it, then the ray cannot hit any of the triangles in the bunny, right? Because the box was built around the bunny. On the other hand, if the ray does hit the bounding box, we're still forced to intersect it with all the triangles. And so we'll make this particular acceleration strategy more sophisticated as we move on in today's lecture, but already you can see why this might save you quite a bit, right? So for example, let's say I have a very high resolution image, like 3x4, and the bunny is only contained within like 1 pixel. Well, according to our previous lectures, what would have to happen? Well, we generate a ray in every single pixel on the image, and every single ray would have to intersect with every single triangle on the bunny. But by using the bounding volume, maybe it looks like that, we can really substantially reduce the number of pixels that have to touch all those triangles when they're trying to figure out their ray object intersections. So if we want to compute a conservative bounding volume, then the bounding volume, of course, needs to be big enough to contain their entire piece of geometry. So here I'm showing you a box that's around the bunny, but this is by no means the only option. So for example, you could use a non-aligned bounding box, so that isn't aligned with the XYZ coordinates. You could use a sphere, an axis-aligned bounding box. This is the one we're going to focus on today. But there are also more kind of sophisticated strategies out there in the universe. For example, maybe some arbitrary convex region where you get a bunch of half planes that you use to bound your space. So there's a little bit of a push-pull here in terms of the best type of bounding region you should use. Obviously, the more tightly your bounding region wraps around your object, the better it'll be in terms of reducing the amount of computation you do after you do your ray bounding region intersection code. But if you have a really complicated bounding region, well, then you might end up spending all of your calculation intersecting your rays with that object. And so there's some kind of simplicity versus, tightness trade-off that happens in this space that depends a lot on the details of your scene and maybe other things about the ray tracing algorithm that we're going to use. So the most common choices for bounding boxes tend to be the really simple ones, like just bounding boxes that are aligned with your axes rather than some fancy convex region that's hard to compute. So today we're going to start easy, and in particular we're going to focus on the case on the lower right, which is a bounding box, which isn't even just a box, but is actually aligned to the XYZ axes. So our first task for today's lecture is to figure out how to intersect a ray with a box. This is, of course, kind of a necessary component of any code that wants to use bounding boxes to accelerate the ray tracer. So first of all, we can describe a box using basically two sets of coordinates, right? This would be like the bottom lower left coordinate and the upper top right coordinate of the box. Typically, we assume that like x1 is less than x2, y1 is less than y2, and z1 is less than z2, just for convenience. And now in addition to this box, we have a ray. And the question we want to answer is, does the ray intersect the box? So maybe the box contains within it the Stanford bunny, and we want to know, do we need to intersect our ray with the bunny or not? So how could we answer that question? Well, the naive thing to do would be to say, well, actually, we already have code for this, right? The box is nothing more than 6 different planes. We could compute the intersections of all of those 6 planes with our ray, and then return the closest one that actually is on the boundary of the box by checking that you're on the proper side of each of these planes. That's perfectly fine, mathematically speaking, but it turns out that we can do better specifically for an axis-aligned bounding box. This isn't that surprising, right? Because sort of the whole point of axis alignment is to make math easier. So let's do that real quick. So there are a few different structures that we can use to make our life a little bit easier when we intersect rays with an axis-aligned bounding box. One is that we have pairs of planes that have the same normal, up to sign, I guess I should say. So for example, notice that like the top and the bottom have the same normal vector, just flipped up and down. Moreover, numerically speaking, the normals only have one non-zero component, right? Either x, y, or z. And then finally, we can kind of do computations one dimension at a time. So for instance, if we never enter the bounding box in the x coordinate and the y coordinate, then we certainly don't need to worry about whether or not we might enter it in the z coordinate. Incidentally, one kind of annoying thing about geometry is that there tend to be a million special cases and boundary cases, and this is no different. One special case that you should just keep in the back of your head is specifically when your ray is parallel to your box. That's a pretty easy one to detect and check, and then, of course, you just need to see whether or not your coordinate is in the inside. I'm not going to worry about that too much. So our strategy for intersecting a ray with an axis-aligned bounding box is going to be to intersect that ray with each dimension, like x, y, and z, one at a time. So let's see what that looks like. So here we have a 2-dimensional bounding box where the x coordinates go from x1 to x2, and the y coordinates go from y1 to y2. So now we have some ray. Remember that our ray looks like r naught plus t times rd. Right? That's our p of t here. So like here's r naught and here's the direction. So there's sort of 2 things that we have to worry about when we intersect our ray with the box. One is, when is the x coordinate in the range from x1 to x2? And the other is, when is the y coordinate in the range from y1 to y2? So we're going to use very similar reasoning to how we did constructive solid geometry a few lectures ago. In particular, the interval of time, in other words, the set of t values in which our ray is inside of the box, is the intersection of 3 intervals. Those 3 intervals are the time when the x coordinate is between x1 and x2, the time when the y coordinate is between y1 and y2, and in 3D, the time when the z coordinate is between z1 and z2. So for example, here's the first interval. So we take our ray, oops, and we just worry about the x coordinate here. And what we get is that for this segment of our ray, the x coordinate is inside of the x's of the box. But notice that our computation isn't done. In particular, this segment, I'm in the proper x range, but the y range is incorrect. So now we can do a second thing, which is compute the interval of times when the y value is in the proper range. And that's shown with this green line here. So during the green time, the y coordinate of the ray is between y1 and y2. So what do? I take those two intervals, I put them on top of each other, and I take their intersection, and that is going to be the actual set of t-values in which my ray is inside of the box. This is exactly the same reasoning we used in constructive solid geometry to compute the intersection of two shapes. So let's look at the same kind of computation in one dimension. So here we can essentially take the x coordinate, the y coordinate, and the z coordinate, and for each one of those compute the interval of time in which the ray is inside of that range. So what's going on here? When is the ray inside of the box? Well, it's inside of the box when all three coordinates are inside of the box. So if we look, that's here. So if we think of this as sort of tx start, tx end, similarly for y and for z, then the start time when you enter the box is going to be the max of the start times for the individual intervals. It's like the max of the mins. This is an easy source of bugs. And similarly, when you exit the box is the min of the maxes of the intervals. So if I compute these three intervals one at a time in my ray tracing ray box intersection code, then all I have to check is the start time, in other words, the max of the mins, bigger than the end time, which is the min of the maxes? And if so, the ray intersects that axis-aligned bounding box. If it's larger than, if start is bigger than end, then it does not intersect the bounding box, and I do not have to check my ray against the objects inside of the box. If start is less than or equal to end, then I do need to recurse. Okay, so slowly we're narrowing down on an algorithm. The last thing that we need is just to compute those start and end times for those x, y, and z coordinates. Of course, this is no big deal. So for instance, let's think about just the starting time here. So let's say that we have, what do we want to do? We want to figure out at what time, for example, does my ray hit x1? Well, what do I know? I know that the x coordinate of my ray looks like r0x plus t times r dx. So if I solve this for t, what am I going to get? I'll get t equals x1 minus r0x, all of that divided by r dx. So what is this value here? This is the time at which the ray enters the x range of the boxes. And we can substitute in x2 and then y1, y2, z1, z2 to get the different values for these different intervals. So by the magic of PowerPoint, here's our formula here. So the interval of time in which x is in the proper range is given by the range between these two t values here. We can do the same thing for y and z, and those are going to be the intervals that we intersect at the end of the day. So we initialize our x interval as the interval of time when the ray is in the box. Next, we compute the interval of time when the y coordinate is in the box, and we update our interval, right, because that's the space that we want. And then, at least in the two-dimensional case, we're done. Of course, in 3D, we have one more iteration to go. Okay, so I think this is one of these things where I'm putting it all on the slides and spelling it all out for you, but that's probably actually making it harder than if I just asked you to intersect a ray with a box at home. I think you guys are all very smart MIT students and could have figured this one out without my help. But it's important to think through these kinds of calculations carefully. Now that we have that interval of time when your ray is in your box, we can think about the different cases that can happen. So for instance, if T start is bigger than T end, then my ray doesn't intersect the box whatsoever. That's what's shown here. If T end is less than the T where the ray starts, like T min, typically that's 0 or maybe epsilon to displace a little bit, well then the box is behind your eye and you don't need to test. And now we do need to intersect the ray with the box, and there's two cases within that, right? One is where you can see the box and you're on the outside. And then there's a slightly different case where your eye is in the inside. But both of those are just equivalent to checking that your T start for your eye is less than T end. Okay, so, I guess your eye is T min. My apologies. In any event, this is a lot of indices and a lot of coordinates, but the reality is that intersecting a ray with an axis-aligned box is not a hard problem, and I'm sure that you guys could all work this out at home. If you like pseudocode, that's given on this slide here, and it's essentially just laying out exactly what we've already talked about. So you intersect your ray with the x interval, the y interval, and the z interval separately, and then you take the max of the start times and the min of the end times, and then essentially these four cases are all the different things that can happen. One tiny hack, remember that we want to squeeze as much efficiency out of our ray tracer as possible, is the following. Do we actually ever need our dx? Well, sort of. I mean, you can see that we divide by it here. One thing that's worth knowing is that division among the different numerical operations is probably the slowest among, plus, minus, times, divide. So one trick that oftentimes ray tracers will do is instead of storing r dx, r dy, and r dz, they'll store the reciprocals of those values and multiply by them. Just a fun trick. Okay, so now we know how to intersect a ray with a box. So now we're cooking with gas, but we got to figure out how to actually find the box that we're going to use as a bounding box for different objects. That's not terribly difficult. So for example, if we want the bounding box of a triangle, all you have to do is take the lower left part to be the min of all the coordinates, the upper right part to be the max of all the coordinates. If I want the bounding box of a sphere, I just have to be a little bit careful about the radius. One object for which bounding boxes are not particularly helpful is a plane, right? Because planes have infinite extent. So the bounding box of an infinite object is basically infinite. And there's one final case that is pretty obvious, but is worth calling out. And that is the bounding box of a group of things. So unsurprisingly, basically for the rest of today's lecture, we're going to end up putting bounding boxes around bounding boxes, and so we'll need to do this calculation a lot. So if I have two different bounding boxes, you see the A subscripts and the B subscripts, then the bounding box of the union of these two objects is given by the formulas we have on this slide. So you take the mins and the maxes of each of the coordinates one by one. One last source of bugs that I thought was worth calling out is to compute the axis-aligned bounding box of a transform. This is a little bit tricky, only because rotating and stretching and shearing can actually create some weird changes to the bounding box when you force it to be axis-aligned. Of course, if you don't care whether your bounding box is axis-aligned, you can just rotate it or transform it with your object. But in this particular case, if you do, then essentially the formula on this slide is just telling you to recompute it. So in particular, you'll transform the four vertices of the past bounding box and then compute the new axis-aligned bounding box of those 4 points. Again, I think all of this stuff looks complicated, right? There's a lot of symbols on the slide here, but if I asked you to code up bounding boxes, you probably wouldn't have a whole lot of trouble as long as your boxes are axis aligned and you're thinking about it. So that's all well and good, and it can reduce the computation of our ray tracer quite a bit. So for instance, I remember in Finding Nemo, there was a big problem, which is that they're filming these underwater scenes, and the artist got kind of excited about modeling little, I don't know, underwater vegetation that's swishing around in the water. But then what would happen is like every pixel would end up intersecting, some big pile of vegetation. And so by just putting a bounding box around an object, at the very least, if your object is nowhere near the pixel that you're rendering, you'll never have to intersect your ray with all the triangles inside of that sea anemone or whatever. But the next question we should ask is, are bounding volumes enough? So let's think about a 1 million triangle mesh here. And let's say that we're kind of rendering it head on. That's a pretty typical scenario. So it could be that we get quite a bit of savings simply by virtue of avoiding having to intersect rays outside of the bunny with any of the bunnies at all. But now, maybe we send a ray down the middle of our image. It intersects the bounding sphere, and suddenly this pixel has a million computations to do before it can intersect with the bunny. That's not so great. And in fact, if the bunny takes up a large part of the image, then we really haven't had all that much savings. So what are we to do here? Well, we're going to use a trick that I think is pretty predictable, which is that it's bunnies all the way down here. In particular, we can put a bounding box around the entire bunny, or in this case, I guess a bounding sphere. And now we can chop the bunny in half and put bounding spheres around those two halves and recursively keep splitting until we get down to a manageable load for computation. Now this strategy is called a bounding volume hierarchy. And the basic idea is that you compute a bounding box for all of your objects, and then you want to split it into two groups, compute the bounding boxes for those child objects, and so on. And so what you end up with is a binary tree, right? So the upper level node of your binary tree is like a box around the entire scene. And then inside of that bounding box are maybe two more bounding boxes containing two chunks of your scene. Inside of those bounding boxes, maybe are two more bounding boxes, and so on. So this is a really nice strategy, and I think it's sort of reminiscent of the strategies that we're used to thinking about in algorithms class. But there are still a few challenges. One is that there are many different ways to recurse here, and we have to choose a good way to keep bipartitioning. But another, which I think is the most common source of bugs, is actually shown on this slide in a reasonable fashion. So when we get to the bottom level of our tree here, one thing that's worth noting is that this triangle is in his own box, but that box actually intersects other objects. And so when we traverse our bounding volume hierarchy, we're going to have to be super careful about that our boxes can actually overlap with one another. So we'll come back to that in a moment. Now, when we're constructing a bounding volume hierarchy, there are many choices to be made, right? So how do you do it? Well, you have your whole scene, maybe a giant pile of triangles, and now you need to split that in half, and then recurse. So in order to do that, one thing you might do is just take that box and literally split its coordinate in half to make a new volume. That can be a little bit dangerous. So for example, let's say that I have a scene with like 4 things, 5 things all the way on the side, and then one object all the way outside. So the bounding box for my scene looks like that. If I split right down the middle, well, I actually haven't really saved all that much computation, right? Because now most of the intersections are still on one side. A slightly more clever technique might, for example, sort the x coordinate and then put exactly half the objects on one side or the other. So in that case, so here's our 5 and then 1 separated thing. So we might number them off and say, well, I want exactly half my objects on one side and half the objects on the other. This is typically a better strategy because it kind of balances the load on the two sides of your bounding volume hierarchy. And then a third thing that sometimes people do is like maybe the shape itself was modeled in a hierarchical fashion, so you just reuse it. So like maybe a bicycle was built out of wheels, the wheels have spokes on the inside, and rather than building a new one for rendering, you just leave it be. Now, no matter what you do, sometimes these strategies don't work. So for example, maybe we have two interlocking puzzle pieces, like here's a letter C and then another letter C, like that. I don't think I'm ever going to find a clever plane that chops this in half so that rays only have to intersect one object or the other. So that's just bad luck. Okay, so that's how to construct one of these hierarchies. The other thing we have to do is actually intersect a ray with a bounding volume hierarchy. And initially, this sounds like an easy piece of code to write, and in a sense it is, but it's one that is a little bit finicky, that you have to get all the details correct or a bug could easily sneak in there. So, based on the first chunk of lecture, we already know how to intersect a ray with a box. That's no big deal. So let's say that we have a bounding volume hierarchy like what I've shown you on this slide. Then what we did at the beginning of lecture can give us like, aha, there are two intersection points with this box. The ray enters the box and we must recurse. Well, as you can see, there's sort of two boxes inside of the larger piece of the bounding volume hierarchy. So what can we do? Well, we can intersect our ray with these two objects. And maybe this is the level where we detect that it intersects this triangle and we're done. Now, there's a thing that's tempting to do, but it turns out to be incorrect. And that's the following. So here's the observation you might make. Let's say that I had a triangle here. Okay, so I went ahead and I recursed on bounding box number 1, and I found, aha, my ray intersects this triangle. So now when I'm done with my recursive call, I say, all right, well, there's already an intersection. So maybe I feel like I don't have to even recurse on bounding box number 2 at all, right? That feels right. And indeed, this case, that would be correct, right? Because this triangle, this little nacho that I've drawn, is basically blocking the ray from entering box number 2 at all. However, that doesn't always happen. So in particular, if you intersect the closer box, that may actually not mean that you don't intersect the farther box. There were a lot of negatives in that sentence, but let's see what that means in practice. So in particular, here's a scene with two bounding boxes in our bounding volume hierarchy. But because the scene is constructed in kind of an evil fashion, take a look at what happens. There is, I really wish that wouldn't happen. There's an intersection between the two bounding boxes, right? So there are 4 blue triangles in the left box and 3 yellow triangles in the right box. And so when we compute the bounding volumes 1 level down in our tree, and then step back 10 feet, we see that unfortunately they share some space. So what goes on here? So remember that our ray has a source point on the lower left, and it's moving up into, it has a source point on the lower right, and it's moving up into the left. So one thing we might do is say, okay, well, the first bounding box in our hierarchy that the ray runs into is this box on the right-hand side. So we'll call that box number 1. Okay, so because it was the first box that we ran into, recurse on all these triangles. And what are we going to find? Well, we're going to find that our ray intersects this yellow point here, right? Because the blue triangle belongs to box number 2. So it's tempting to say, okay, well, the first box in my bounding volume hierarchy that my ray runs into is box number 1. I hit a triangle in box number 1, so I don't even look inside box number 2 to find an intersection. But here you can see that that's actually incorrect. In particular, there is an intersection in box number 2 that I would miss with that strategy. And so the reality is that when you want to intersect a ray with a bounding volume hierarchy, you actually need to intersect with just about everything when you recurse, just to be on the safe side. So the one time where you don't have to recurse is when your ray doesn't touch the bounding box at all. Okay, so let's talk about bounding volume hierarchies and summarize their advantages and disadvantages a little bit. The advantages of a hierarchy like this is that it's pretty easy to construct, right? This is a binary tree construction that kind of follows what we showed. And it's also easy to traverse. But the disadvantage is that it can be quite hard to choose a good way to split the objects in half to make a particular node. And then a bad split could mean that it's actually quite hard to do any pruning, meaning as you move down this tree, you have to look left and right. That said, it's still a pretty reasonable method. It's easy to code, relatively efficient, so it has the 6837 stamp of approval for something you can try on a first shot. So for example, on your rendering homework, if you want to make it faster, this would be one of the easier strategies to implement. But now let's talk about another strategy that looks quite similar, but the details make it so that the behavior is quite different from bounding volume hierarchies. And that is using KD trees. This is probably the most popular acceleration structure. Certainly if you take a computational geometry course here at MIT, you'll encounter a KD tree quite a bit. So here is going to be the main difference between a KD tree and a bounding volume hierarchy. In a bounding volume hierarchy, the boxes could overlap, but every object belonged to exactly one box at the bottom level of the tree. In a KD tree, objects can basically intersect with more than one box, but the bounding boxes don't intersect. Okay, so the idea is that sometimes you'll have an object that touches more than one bounding box, and that's okay. We'll just add it to both of them. But the boxes don't overlap. We never have a case like that where it touches one of the other things. So the way that we're going to construct a KD tree is to just keep making axis-aligned splits. So we'll have an axis-aligned bounding box for our whole scene, and then maybe we split it in half. Now those two halves, we can find some plane and split those in half. Maybe these ones we also split in half. By the way, when I say half, I don't mean geometrically necessarily, and so on. So this is a space partition. The nodes, like the boxes at the bottom level of the tree, do not overlap. So a data structure for KD trees, like here's some not quite C++ pseudocode, is pretty easy. So again, it looks like a tree. There are two nodes. I think actually front and back is a little misleading because depending on what side you view it, the idea of front and back swaps, but whatever, there's child 1 and child 2 here. Each of these KD tree nodes can store a few things. First, it stores which dimension gets split, like the X, Y, or Z. And the distance of the split may be from, the corner of the box. So the distance here would be there. And notice that it's splitting along the X because I moved to a particular X coordinate and then I do a vertical line. And if you're a leaf, meaning that there are no boxes inside of you, you also have a list of triangles that are sitting inside of that node of the KD tree. Okay, so we have to do two things, just like when we talked about bounding volume hierarchies. First, we have to tell you how to make a KD tree, and second, we have to tell you how to intersect an array with a KD tree. So let's talk about how to make a KD tree. So here's what we can do. We're going to start with the biggest bounding box we can. So just a box that goes all the way around the scene here. And now we're going to have a recursive algorithm. So we have a list of all of the objects that we need. And we're going to look at it and we're going to decide two different things. One is which dimension to split. So for example, to draw a vertical line or horizontal line. The other one that we have to do is to decide where to place that line. In other words, the distance to split, maybe from the side of the box. So in order to choose the dimension, this is usually a pretty easy decision. Like a good heuristic might be to just use the longest dimension so that you never get a really wild and crazy long rectangle. But to decide on the location of the split, that's a much more tricky consideration. And it's really quite difficult to do. And we're going to talk about a few strategies in a moment. So one thing that I need to note right now is that it may be impossible to find a split that cleanly separates all of the objects on one side or the other. So for example, here, this green triangle, we've decided on a particular split, and this triangle intersects both sides of the box. Well, then what's going to have to happen is when we recurse and split the left and right bounding boxes, we'll need to do that in a way that is aware of that triangle on both sides. So we keep recursing, and eventually every box will contain some minimum number of primitives, and then you just stop the recursive procedure, or maybe there's some other stopping criterion, like, I don't think I'm going to ever look at this box, so I don't care if it's got a lot of really complicated stuff in it. This discussion might sound fuzzy, and that's because it is. There are many different heuristics and strategies people use to construct KD trees in practice. So on the slides here, I've given you guys some references into discussions of this particular consideration. Let's talk about how to traverse a KD tree at a high level. So the basic point here is that we may need to recurse on the children of one of the nodes of our KD tree if our array intersects either of those nodes. So for example, a very simple thing I could do would be intersect our array with the two bounding boxes, just one at a time. And if the array intersects the front bounding box, then recurse on the front one. If it intersects the back bounding box, recurse on the back one. And just don't worry about if we can reduce calculation. And conveniently, we already have code for intersecting array with a box, so maybe that's good enough. But that turns out to be a bit of a redundant calculation. In particular, there's sort of two reasons. One is that these two boxes share a wall, so we probably don't need to recompute the t for the intersection. The other is that if I intersect the front box, I may not need to recurse in the back box at all. So let's dig into that a little bit. In particular, one thing we can do is talk about a slightly smarter version of KD tree traversal. So what we can do is during recursion, we're going to get some information as input. Namely, we're going to know the start time and the end time where our array enters and leaves the box respectively. Now, the only piece of missing information is the time t where our array intersects the wall inside of the box, and this is pretty easy to compute because our box is axis aligned. So again, we have three values, the t start, t end, and t, each of which basically involve the three planes of the box that the array is entering and leaving. So what do? Well, given these three values, essentially we can figure out whether we're in three different cases. And those are illustrated on this slide. You could just intersect the front box, you could intersect the front and the back box, or just the back box. Or I guess you might not intersect the box at all, but of course, because you've already recursed here, that actually can't happen. So how can we detect these three different cases? Well, let's think about it for a minute. Remember that t start is when you enter the bigger box, and t end is when you exit the bigger box, and t is when you intersect this plane. So let's say that t is bigger than t end. That would be kind of like case 1, right? Where you enter the box, you exit the box, that's time t end, and then you reach the wall in between the two sides of the KD tree. Case 2 is sort of the opposite of that. So t start is when you enter that outer box, t end is when you leave. So notice that the time where you hit that wall in the middle of the box is actually before you enter it. So in this case, you only need to intersect with the back. Or in all the other cases, you got to intersect with the back and the front. So here's some pseudocode for traversing a KD tree. So first of all, if you're a leaf, well, then you just kind of leave the KD tree and intersect with all the objects sitting inside of that node. And otherwise, you need to compute the t at which your array intersects the box. And there's three different cases, right? One is where you only have to traverse the back node. Another is where you only have to traverse the front node, just like we showed on that slide. And finally, that last case is indeterminate, right? You have to traverse both the front and the back. But in this third case, we can still do something kind of sneaky. We're going to first traverse the front node in our KD tree. So in other words, we're going to intersect just this interval on the left. And now, if we hit something, unlike in the bounding volume hierarchy, we can actually stop. We can do early ray termination and leave. So we only intersect with the back part in this third case when we didn't find anything in the front part. The reason that we could do that is that we know that our bounding boxes don't overlap. This is different from the bounding volume hierarchy, and it's a nice way to get a little bit of savings in our KD traversal code. And so this basic idea is called early termination for obvious reasons. The basic point here is that I can often quit out of my KD tree traversal before intersecting with different objects by convincing myself that my ray couldn't possibly hit something in the other box. And essentially these different tricks allow ray casting to be reasonably independent of the depth complexity of your scene. In other words, like just the craziness per pixel here. So that's the main idea, is that there's two big gains that you get by using a KD tree. One is you only intersect with nearby triangles, and the other is that if you have two boxes and you intersect something in the first box, you don't have to intersect something in the second one. And those are basically boxed on the slide here, right? So here we're able to eliminate entire bounding boxes worth of information by just realizing our ray doesn't even hit them. And here we're saying by intersecting the front box, if we found something, we know we don't have to intersect the back one. Of course, there are many implementation details. If you're at a leave and you intersect an object, but the object gets intersected outside of the box, then you should actually report that there is no intersection. So for example, let's say here's a bounding box and here's a triangle. Oh, this is hard to draw. And I have a ray like this one. Then yes, it is true that the ray intersects the triangle, but it does not do so inside of the box where I'm currently recursing. So I'm going to say there's no intersection. Otherwise, your tree traversal algorithm can pretty easily fail. Another one, this I think is the most common source of annoyance. We use the term front and back, but if I have a KD tree node like that, then the label of front and back depends on what side I'm on. And then finally, there's a bit of degeneracy if your ray is like parallel to the side of the box. It's easy to ignore this case, but it actually can happen because artists tend to model scenes in a nice axis-aligned way. So there's one hanging thread that we didn't discuss, which is choosing where to split when you construct a KD tree. There are many different heuristics here. Essentially, you're trying to build a KD tree so that at the end of the day, your ray tracing algorithm is as efficient as possible for your scene. And that's a tricky matter. So for example, in this simple baseline, which I think was obtained basically by just splitting stuff in half, notice that actually it does okay because the ray just traversed our scene very easily. But if our KD tree doesn't really conform to the ray tracing we expect to do, then like here we ended up doing a bunch of different ray box intersections that were all kind of unnecessary because the ray doesn't touch anything at all. And so there are lots of different strategies that people use here. Some simple one kind of similar to what we talked about for bounding volume hierarchies might be to split in the median coordinate. This is some attempt to balance a tree, but it can lead to an imbalance between empty and dense areas like what you see here. And there's all kinds of other heuristics. So one of the ones that a lot of people use is something called a surface area heuristic, which roughly says that I want, if I took all the objects in my scene and I projected them onto a wall of one of the boxes in my KD tree, what matters is splitting up that surface area. So if two different objects kind of occupy the same piece of the wall, then I only want to account for it one time. So this is outside of the scope of 6837, but I encourage you guys to do a little extra reading because there's all kinds of clever tricks here. And really it is important to optimize where those splits are. So they can have up to a 2x factor of improvement over naive strategies for making a KD tree. Something that's worth noting is if you take an algorithms course, there are really clever ways to construct KD trees that people use to try and, for example, bound the worst case traversal of your tree. Many of those do propagate into graphics, but we also use a lot of heuristics that would be hard to prove something about, but seem to work well specifically for the scenes that we are animating in 3D. Now, you can go really crazy with making ray tracing faster, and specifically working with KD trees is something that's been well explored in the graphics world. If you like this kind of thing, I strongly encourage you guys to do lots of outside reading and maybe even explore it in your course project. So for example, a good reference is Ingo Wald's PhD thesis, which includes optimized ray triangle intersection, ways to store KD trees to take a little bit less memory by doing weird tricks involving bits in values, and a bit of parallel extensions. And this seems painful, but the reality is that ray tracing does so many calculations and so many rays get sent out in a ray tracer that even small amounts of time you can shave off to in this ray scene intersection operation are worth it. So at the end of the day, there are many different pros and cons to KD tree traversal. On the one hand, it's also not too difficult to code, although it's prone to kind of goofy errors if you're not paying attention. And it's easy to traverse a KD tree. This con I want to mention is also true for bounding hierarchies, a little bit less so, but certainly true for KD trees. Essentially, let's say that I spend a ton of time optimizing for like a super cool KD tree that, perfectly splits the objects into two buckets every single time I recurse and is optimized to reduce the amount of calculation per ray to like near zero when I do that ray tracing step. There could be a problem here, which is I might spend so much time constructing my KD tree that time actually ends up dominating the amount of time it takes to do the rendering, right? Because notice that now your rendering algorithm kind of happens in two steps, right? The first step is the tree, and then the second step is the ray tracing step. And these really happen one and then the next, right? Because the same KD tree for a 3D scene is used for every single pixel during the ray tracing stage. So what does that mean? Well, there's some balance you have to hit in the amount of time that you take in these two steps, right? You could put a lot of computation into computing a really good tree, and then the ray tracing step is a lot faster. Or you could construct kind of a bad tree, and the ray tracing step is somewhat faster. And that trade-off is really, really hard to understand in practice. The reason why is that in some sense, this is an example of amortized analysis. And what does that mean? That means that we typically think of the complexity of ray tracing as somehow scaling with the number of pixels, but this first step doesn't. So when you take the computation time into account for constructing the tree, you might want to like divide it by the number of pixels or something to figure out a rough estimate of whether it's worthwhile. So for example, if I'm rendering a scene with 1 pixel, constructing a KD tree of that scene is probably unnecessary. That's obviously an extreme example, but hopefully you get the point. So in our last bit of time here, I thought I'd discuss one more way that you can accelerate this ray scene intersection operation, which is somewhat in between these past two strategies, but it has a very different flavor. And that's something called ray marching. So both in the bounding volume hierarchy and in KD trees, essentially we built a recursive structure, right? We have one bounding box around the scene. That thing contains 2 bounding boxes. Each of those bounding boxes contain 2 bounding boxes, and so on. Where the difference was that in bounding volume hierarchy, they can overlap, and in KD trees, they can't. But in bounding volume hierarchy, objects belong to one leaf node, and in KD trees, they belong to more than one. There's a different strategy, which feels a little brain dead, but is actually almost more compatible with, for example, your graphics card, depending. And that is something called ray marching. I think this is a little bit less common than some of the other strategies, but it's kind of a fun one to mention. So in ray marching, we're going to use a different way to construct boxes. They're not going to be bounding boxes at all. Instead, what we're going to do is take a giant grid and just overlay it on top of our 3D scene with no regard, or very little regard, for the geometry in our scene. Okay? And what we're going to do is anytime that an object intersects one of the grid squares, we're going to add a pointer to it to that grid square. So the same triangle could easily be a member of several different squares in this grid here. Now, the cool magic trick that we're going to do in ray marching, oh no, now I've drawn on top of this thing, is that essentially when we ray trace, we're going to start at one box, and we're just going to kind of march along these boxes and intersect our rays with them one at a time. I'll add some detail about that in a minute. So the first step of ray marching is to create a grid over the entire scene. There's a parameter here, which is the grid resolution, so like the number of boxes in the X, Y, and Z coordinates. Obviously, if that number is too small, then ray marching really doesn't do anything. But if it's too big, then you actually will end up with an extremely dense data structure. Like the same triangle could be a member of 1,000 different boxes. So after we create our grid, we're going to insert all the primitives into it. So essentially, we have to be a little bit careful here. So if a triangle intersects more than one grid square, then we add a pointer to that triangle to all of the different cells in the grid that it overlaps. Now, optionally, out of laziness, we often do this with bounding boxes. This isn't 100% necessary, but for example, a typical implementation might actually add this triangle to this bounding box, even though they don't actually overlap. I think for triangles, this isn't necessary, but for complex shapes, it might be. So the basic idea here is that there is a one-to-many relationship here, right? So each cell can contain pointers to many triangles, and each triangle can be a member of multiple cells. Does that make it a many-to-many relationship? I'll have to think about that one. In any event, now let's talk about rendering. So first of all, version 0 here could simply eliminate cells in our ray marching algorithm that don't ever touch our ray. So for example, here we know that these rays that these boxes that I'm shading in here never intersect the ray, so we don't need to test with the objects inside of them. But instead, we're going to use a more clever trick than that. And this is going to be called marching. So essentially, what we're going to do is figure out the cell in which our array first intersects the bounding box of the entire scene. We'll intersect with all the objects inside of that box. If we found something, great, we're done. We can return and we don't need to do any other intersection. Otherwise, we'll say, okay, well, this box is empty or it doesn't intersect our array. So now we find the second box that our array intersects. We do the same calculation. In this case, nothing happens. So we move to the third, the fourth, the fifth, and so on. So that's going to be our basic trick. Now, there's a few things that are worth noting. One is that, so for example, this triangle here is a member of multiple cells. You may wish to remove some redundant computation by marking your object as okay, I already intersected my array with it. I don't need to do that again. It's actually more typical to not even bother with that because, for example, otherwise you're going to have to reset the mark every time you want a new ray to go into your ray trace scene. But there's some other things that we can do to make this a little bit faster. Right. So, and one additional thing that I should note is that, of course, similarly to the KD tree, we have to be careful not to report distant intersections. So if I enter this cell here, it is true that the triangle I just drew an X on intersects that cell, but and it intersects the ray right here, but it doesn't intersect the ray inside of the cell. So I've got to keep moving in my marching algorithm. So the last thing that we need to think about when we talk about ray marching is essentially which cells do we want to examine here. Now, it's very clear that we don't need to examine boxes that don't intersect the ray at all, but we can actually do better than that. In other words, we do not need to intersect our ray with every single voxel in the scene. So what do? We start with intersecting the outer bounding box. We find the T-min where that happens. I already mentioned that. And now, essentially, we're going to just keep computing iterative cell crossings from one to the next. The kind of cool thing is there's actually a nice pattern to where that happens, because notice that like the times where you intersect the X walls happen at regular intervals, and the times when you intersect the Y walls also happen at regular intervals. That's what's shown on the slide here. And you can compute those sort of DTs. And so essentially you'll just keep incrementing by these things to figure out the next cell that you intersect, right? So we can compute the next X and the next Y cell from where you currently are in T, and that'll tell you whether to move up or to the right. This is an example of the three-dimensional digital difference analyzer algorithm. So DDA used to be like how you draw a straight line on a computer. So if you play with MS Paint, then a similar algorithm is being used to draw lines without like iterating over all the pixels on your whole image and figuring out which ones are along a line. And essentially all they do is they start at one corner of a line and just iteratively move up and to the right in a way that finds all the pixels that intersect that line. And this is a pretty straightforward trick, and it's also the one that we'll use in our ray marching algorithm to figure out which cells in your ray marching grid you actually have to intersect your ray with. So at the end of the day, here's your pseudocode for ray marching. You create your grid, you insert the primitives into grid squares that intersect the primitive, even if that happens more than once. And now for each ray, you figure out where the ray enters the box, and you start marching up and to the right until you run into something, and then you stop. And that's basically it. So here's a visualization of what the ray marching algorithm looks like. So maybe you can see, for instance, here, the different voxels that your ray intersects, and you never have to touch a voxel that essentially your ray doesn't pass through. So what are the advantages and disadvantages of this technique? Well, this is extremely easy to construct and easy to traverse, right? You're just moving up and to the right. But you might move through a lot of empty boxes, and the geometry might still be clumped. Like you might have one cell inside of this thing that just contains a ton of objects. So in any event, to recap a little bit, the basic issue and the reason that ray tracing is so slow is because you're tracing a lot of rays. And the main bottleneck of the algorithm as we've described it so far is intersecting every ray with every primitive. So the basic strategy that we've used today to get around that is to make use of bounding volumes. In other words, to just draw a big box around a whole collection of objects in our scene. And if our ray does not intersect that box, then we don't need to intersect the ray with anything inside of that box. And we talked about 3 different algorithms that leverage that structure. In a bounding volume hierarchy, we have boxes that can overlap, but every object belongs to at most one leaf node. In a KD tree, the boxes don't overlap, but we have to add objects to more than one leaf node. And then finally, the ray marching algorithm is kind of its own thing, right? You put a big grid on top of your whole scene, and the advantage there is that the boxes are laid out in this very regular way, which allows you to march from one to the next in a very straightforward fashion. So that'll do it for our discussion of efficient ray tracing. You should know that this is really just the tip of a gigantic iceberg. People design all kinds of really clever techniques to make ray tracers faster, and it continues to be a topic of study. One particular challenge is that the algorithms we've talked about today make use of structures like trees and so on. These are built on recursive techniques. And of course, recursion is not particularly compatible with the architecture of your computer graphics card in your machine, right? Your computer graphics card doesn't like to have special cases and if statements and all that good stuff. And that's really the main challenge in efficient ray tracing on your GPU. That's a modern topic of study, and new technologies are coming out every year that make that even faster and more interesting. So with that, we'll stop, and I'll see you next time.